At the smallest scale, reality breaks its own rules. Subscribe. Quantum truth starts now. Decoding the universe begins not with galaxies or stars, but with a question so small it almost escapes notice. A question humanity did not even know how to ask until the last century. A question that whispers rather than shouts, what is reality made of when we zoom in far beyond atoms, beyond molecules, beyond anything the human senses evolved to understand, into a realm so tiny that the rules governing our everyday lives collapse, and something profoundly stranger takes their place? Because when we look closely enough at the fabric of existence, the universe stops behaving like a machine and starts behaving like a mystery, and this is the threshold of the quantum world, the place where classical intuition dies and a deeper, more unsettling truth is born. A truth that challenges our ideas of space, time, causality, and even observation itself. Because here particles are not objects but probabilities, locations are not fixed but smeared across possibility, and cause and effect no longer march in a simple line. And to understand how we arrived at this realization, we must first understand the limits of the physics that came before it, the physics of Isaac Newton, and the classical worldview that dominated science for more than 200 years, a worldview that treated the universe like a perfectly wound clock, predictable, deterministic, and ultimately knowable if only one measured carefully enough, where objects had definite positions and velocities, forces acted locally through space, and time flowed uniformly for everyone, everywhere. And for centuries this model worked spectacularly well, allowing humans to predict planetary orbits, build bridges, launch cannons, and eventually send machines into space. But beneath this success lurked cracks that grew wider as experiments became more precise, cracks that appeared when scientists began probing the behavior of light, heat, and matter at extremely small scales, where classical physics began to give answers that were not merely wrong but nonsensical, answers that violated experiments again and again, forcing a painful realization that the universe was not obligated to conform to human expectations. And the first major fracture appeared at the dawn of the 20th century, when physicists studying blackbody radiation, the glow emitted by heated objects, discovered that classical equations predicted an infinite amount of energy at short wavelengths, an absurd result known as the ultraviolet catastrophe, which suggested that the universe would instantly destroy itself with infinite radiation, something clearly not happening. And it was here that a reluctant revolutionary named Max Planck made a desperate mathematical assumption, proposing that energy could not vary continuously but instead came in discrete packets, which he called quanta, a word meaning how much. And although Planck himself initially believed this was merely a trick, a convenient calculation device, it would soon become the seed from which quantum mechanics would grow, because in this simple idea, that nature at its most fundamental level is granular rather than smooth, lay a profound shift in how reality itself must be understood, and the next blow to classical certainty came from Albert Einstein, who in 1905 proposed that light itself behaved not only as a wave, as had long been established, but also as a particle, later called the photon, to explain the photoelectric effect, where light striking a metal could eject electrons only if the light exceeded a certain frequency regardless of its intensity, a phenomenon impossible to explain with classical wave theory, and Einstein's explanation confirmed that energy was indeed quantized, existing in discrete packets, a realization that would earn him the Nobel Prize and further erode the foundations of classical physics. But this was only the beginning, because as scientists pushed deeper into the atom, they found that electrons did not orbit nuclei like miniature planets, as early atomic models suggested, but instead occupied fuzzy regions of probability, standing waves of possibility rather than solid trajectories, and this revelation forced physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger to develop a new framework entirely, one that replaced certainty with probability and determinism with statistics. And at the heart of this framework lies the concept of superposition, the idea that a quantum system can exist in multiple states at once until it is measured, meaning that an electron can be in several positions simultaneously, a particle can spin up and down at the same time, and a quantum bit, or qubit, can represent both 0 and 1 simultaneously, unlike a classical binary bit which must be one or the other. And this is not metaphor or philosophical abstraction, but a mathematically precise and experimentally verified description of how nature behaves at the smallest scales, confirmed again and again in laboratories around the world, yet deeply counterintuitive, because our brains evolved to understand a world where objects are either here or there, moving or still, alive or dead, not a world where reality exists as a cloud of probabilities that collapse into a single outcome only when observed. And this brings us to one of the most unsettling features of the quantum universe, the role of observation itself, because in quantum mechanics, measuring a system is not a passive act, but an intervention that fundamentally changes the system being measured, a phenomenon dramatically illustrated by the famous double-slit experiment, where particles such as electrons or photons fired at a barrier with two slits create an interference pattern characteristic of waves when not observed, but behave like discrete particles passing through one slit or the other when detectors are placed to observe them, suggesting that the act of measurement forces the system to choose a definite state, a result that is fueled philosophical debates for decades about the nature of reality, consciousness, and whether the universe exists independently of observation, debates that continue to this day, but regardless of interpretation, the experimental facts are undeniable. Quantum systems behave differently when observed, and this alone marks a radical departure from classical physics. But the strangeness does not stop there, because even more shocking is the phenomenon Einstein derisively called spooky action at a distance, now known as quantum entanglement, where two or more particles become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are separated, even across galaxies, and this connection appears to transcend space itself, violating classical notions of locality and seemingly contradicting Einstein's own theory of relativity, which states that no information can travel faster than the speed of light. Yet experiments beginning with John Bell's inequalities and continuing through increasingly sophisticated tests have repeatedly confirmed that entangled particles exhibit correlations that cannot be explained by any local hidden variables, meaning that the universe at a fundamental level is non-local, woven together by connections that ignore distance, a realization so profound that it forces us to rethink what it means for objects to be separate at all, because in the quantum universe, separation is not absolute, and this interconnectedness is not merely a philosophical curiosity but a practical resource, forming the foundation of emerging technologies such as quantum computing, quantum cryptography, and quantum sensing, technologies that exploit superposition and entanglement to perform tasks impossible for classical machines. And to understand why these technologies are so powerful, we must understand the difference between classical and quantum information, because classical computers process information using bits that exist in one of two states, 0 or 1, off or on, and all computation ultimately reduces to sequences of these binary decisions, but quantum computers use qubits that can exist in superpositions of 0 and 1, allowing them to process many possibilities simultaneously, and when qubits are entangled, the state of one is correlated with the state of others in ways that allow quantum algorithms to explore vast computational spaces more efficiently than classical algorithms ever could, offering exponential speed-ups for certain problems such as factoring large numbers, simulating quantum systems, and optimizing complex networks. And while large-scale, fault-tolerant quantum computers remain a formidable engineering challenge, small quantum processors already exist and are improving rapidly, signaling a technological revolution comparable in impact to the invention of the transistor. But quantum mechanics has already transformed our world in ways most people never notice, because the digital technologies we rely on every day, from smartphones to GPS, depend on quantum principles to function, and GPS in particular offers a striking example of how quantum physics and relativity intersect in practical technology. Because GPS satellites rely on extremely precise timekeeping provided by atomic clocks, such as cesium clocks and newer strontium optical lattice clocks, which measure time by counting the oscillations of electrons transitioning between energy levels in atoms, transitions governed by quantum mechanics, and these clocks are so precise that they would lose or gain less than a second over billions of years. Yet even this extraordinary precision must account for the effects of Einstein's relativity, because satellites moving at high speeds and experiencing weaker gravitational fields tick at different rates than clocks on Earth, and without correcting for these relativistic effects, GPS errors would accumulate at a rate of several kilometers per day, rendering the system useless, meaning that every time a smartphone calculates your location, it is silently confirming the predictions of both quantum mechanics and general relativity, two theories that together describe the universe with unprecedented accuracy, yet remain fundamentally incompatible at their deepest levels. A tension that represents one of the greatest unsolved problems in physics, because while quantum mechanics governs the subatomic world and general relativity governs gravity and the large-scale structure of space-time, we still lack a unified theory that reconciles them, a theory of quantum gravity that would describe phenomena such as black holes and the Big Bang, where extreme densities and energies demand both frameworks simultaneously. And this quest has led to ideas such as string theory and loop quantum gravity, speculative but mathematically rich attempts to decode the deepest structure of reality. Yet even without a final unification, quantum mechanics continues to reveal astonishing truths about the universe, including the existence of quantum fluctuations, tiny random variations in energy that occur even in empty space, giving rise to a restless vacuum that seethes with virtual particles popping in and out of existence, fluctuations that played a crucial role in the early universe by seeding the formation of galaxies and cosmic structure, meaning that the large-scale universe we observe today is in part a magnified imprint of quantum randomness from the first moments after the Big Bang. And this connection between the smallest and largest scales of reality underscores the profound reach of quantum physics, showing that it is not confined to laboratories but woven into the very history of the cosmos. And this brings us to gravitational waves, ripples in space-time predicted by Einstein a century ago and first detected directly by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a triumph of experimental physics made possible in part by quantum technologies, because LIGO's detectors must measure changes in distance smaller than 1,000th the diameter of a proton, a sensitivity so extreme that quantum noise becomes a limiting factor, requiring techniques such as squeezed light, a quantum state of light that reduces uncertainty in one measurement at the expense of another, to enhance precision, demonstrating once again that quantum mechanics is not an abstract theory, but a practical toolkit for exploring the universe, allowing us to listen to the echoes of colliding black holes billions of light-years away, events that reshape space-time itself. Yet even as quantum mechanics enables us to probe deeper into reality, it continues to challenge our understanding of what reality actually is, because, unlike classical physics, it does not tell us what will happen with certainty, but only the probabilities of different outcomes, and this probabilistic nature is not due to ignorance or experimental error, but appears to be an intrinsic feature of the universe, leading some to suggest that determinism is an illusion, that the future is not fully determined by the past, and that chance plays a fundamental role in the unfolding of existence. A notion that unsettles not only physicists but philosophers, theologians, and anyone who seeks a universe governed by simple, predictable laws. Yet others argue that underlying determinism may still exist in hidden variables or in the branching universes of the many worlds interpretation, where every quantum measurement spawns multiple realities corresponding to each possible outcome, an idea both mind-bending and controversial. But regardless of interpretation, the experimental success of quantum mechanics is unmatched, making it one of the most accurate theories ever devised, confirmed to extraordinary precision in countless experiments. And as we stand at the threshold of a new quantum age, with quantum computers, sensors, and communication networks poised to transform technology, it is worth remembering that this revolution began not with grand ambitions, but with humble questions about why heated objects glow and why light knocks electrons from metal, questions that revealed a universe far stranger and more beautiful than anyone had imagined. A universe where reality is not a static stage, but a dynamic interplay of probabilities, where observation matters, where connections transcend distance, and where the tiniest scales shape the largest structures. And this is only the beginning, because to truly decode the universe we must journey further into the quantum realm, exploring the mathematics, experiments, paradoxes, and technologies that continue to redefine our understanding of existence itself. And in the chapters ahead we will dive deeper into superposition, entanglement, timekeeping, quantum computing, and the future of quantum science. But for now we stand at the doorway, having glimpsed the strange foundation upon which reality is built, a foundation that invites us not merely to observe the universe, but to question what it means to know it at all. As we move deeper into the quantum universe, the strange ideas introduced earlier begin to reveal not only how nature behaves, but how time itself is measured, manipulated, and ultimately redefined by quantum laws, because at the heart of modern civilization lies a silent rhythm, a ticking so precise that entire technologies depend on it. And this rhythm is governed not by gears or pendulums, but by quantum transitions inside atoms, transitions so stable and repeatable that they allow us to define a second with unimaginable accuracy. And to understand this, we must first return to superposition, the cornerstone of quantum mechanics, because superposition is not merely a bizarre feature of microscopic particles, but the very reason quantum systems can serve as the most accurate clocks ever created, as well as the engines of quantum computers, since in quantum mechanics every measurable property of a system, whether position, momentum, energy, or spin, is described by a wave function, a mathematical object that encodes all possible outcomes and their probabilities. And when a system exists in superposition, it means that this wave function includes multiple possible states at once, all coexisting until an interaction forces the system into a definite outcome. And this abstract idea becomes strikingly concrete when applied to atomic clocks, because an atom such as cesium or strontium possesses electrons that can occupy distinct energy levels, and the transition between these levels occurs at an extraordinarily stable frequency, governed by fundamental constants of nature, meaning that each oscillation is identical everywhere in the universe. And when scientists build an atomic clock, They are essentially counting these quantum oscillations using lasers or microwaves to induce transitions and locking an external oscillator to match the atom's natural rhythm. And in the case of the cesium clock, which defines the official SI second, this frequency is exactly 9,192,631,770 oscillations per second, a number so precise that it anchors global timekeeping, yet even cesium clocks are now being surpassed by optical lattice clocks based on strontium or ytterbium, which operate at much higher frequencies and therefore achieve even greater precision, reaching levels where time can be measured so accurately that a clock placed at your feet will tick slightly slower than one at your head due to Earth's gravitational field, a direct demonstration of Einstein's general relativity, showing that time itself is affected by gravity. And this means that quantum mechanics and relativity are not separate domains but intertwined in practical devices, because without quantum superposition and discrete energy levels, atomic clocks would not exist, and without relativistic corrections, their precision would become a liability rather than an asset, causing navigation systems like GPS to fail, because GPS satellites orbit Earth at high speeds and higher altitudes, experiencing both time dilation due to motion and gravitational time dilation due to weaker gravity, effects that together amount to a discrepancy of about 38 microseconds per day, which may seem insignificant, but would translate into positional errors of kilometers if uncorrected. And so, every time a GPS receiver determines your location, it relies on quantum transitions inside atoms combined with relativistic equations describing spacetime, silently confirming two of the most revolutionary theories in physics. Yet this extraordinary precision also reveals something unsettling, because it shows that time is not a universal constant flowing identically everywhere, but a dynamic quantity shaped by motion, gravity, and quantum measurement. And when we push this idea further, we encounter the quantum limits of measurement itself, because Heisenberg's uncertainty principle tells us that certain pairs of physical properties, such as position and momentum or energy and time, cannot be simultaneously known with arbitrary precision, not due to technological limitations, but because nature itself imposes these limits. And this uncertainty is not noise to be eliminated, but a fundamental feature of reality, arising from the wave-like nature of quantum systems. And while this uncertainty might seem like an obstacle, quantum engineers have learned to harness it through techniques such as quantum squeezing, where uncertainty is redistributed between variables to improve precision in specific measurements, allowing detectors like LIGO to surpass classical limits and observe gravitational waves, ripples in spacetime produced by cataclysmic cosmic events such as merging black holes and neutron stars. And these detections mark a profound moment in human history, because they allow us to sense the universe not through light, but through vibrations of spacetime itself, vibrations measured using laser interferometers so sensitive that they must contend with quantum fluctuations of light and mirror motion, requiring quantum theory not just to interpret the signal, but to make the measurement possible at all. And this interplay between quantum mechanics and cosmic phenomena illustrates a recurring theme. The smallest scales of reality shape our ability to observe the largest, and nowhere is this more evident than in quantum computing, where superposition and entanglement are transformed from abstract concepts into computational resources, because unlike classical computers that process information sequentially using bits constrained to 0 or 1, quantum computers manipulate qubits that exist in superpositions of both states simultaneously, allowing quantum algorithms to explore many computational paths at once. And when qubits become entangled, Their states are correlated in ways that allow information to be distributed non-locally across the system, creating a form of parallelism that has no classical equivalent. And this is not mere speed, but a fundamentally different mode of computation, one that allows certain problems to be solved exponentially faster than classical methods, such as factoring large numbers using Shor's algorithm or searching unsorted databases using Grover's algorithm. And while today's quantum computers are still limited by noise, decoherence, and error rates, they already demonstrate capabilities beyond classical simulation, hinting at a future where quantum processors become indispensable tools for chemistry, materials science, cryptography, and optimization. Yet this promise comes with profound challenges, because quantum systems are exquisitely sensitive to their environment, and any unwanted interaction can destroy superposition and entanglement in a process known as decoherence, effectively forcing the system back into classical behavior. And overcoming decoherence requires extreme isolation, precise control, and sophisticated error correction techniques, pushing engineering to its limits and revealing just how fragile quantum states are. And yet, despite this fragility, quantum effects persist everywhere in nature, shaping chemical reactions, biological processes, and even the stability of matter itself. Because without quantum mechanics, electrons would collapse into atomic nuclei and chemistry would not exist, meaning that the solid world around us is stabilized by quantum rules that prevent matter from imploding, and this realization underscores a paradox. Quantum mechanics is both profoundly strange and utterly essential, alien to intuition yet responsible for the very existence of everyday reality. And this paradox deepens when we consider the role of information in quantum theory, because in classical physics, information is passive, a description of a system rather than a physical entity. But in quantum mechanics, information becomes physical, constrained by fundamental laws and capable of influencing what is possible, as demonstrated by the no-cloning theorem, which states that an unknown quantum state cannot be copied perfectly, a limitation that underlies the security of quantum cryptography, where attempts to intercept quantum keys inevitably disturb the system and reveal the presence of eavesdroppers, offering theoretically unbreakable communication. And this shift from energy and matter to information as a fundamental concept marks a deeper transformation in how physicists understand the universe, suggesting that reality itself may be best described not as particles moving through space, but as information evolving according to quantum rules, an idea echoed in theories that connect quantum mechanics to black holes, entropy, and the nature of space-time. Because black holes present a unique testing ground for these ideas, as they combine extreme gravity with quantum effects, leading to puzzles such as the black hole information paradox, which asks whether information falling into a black hole is destroyed or preserved, a question that strikes at the heart of quantum theory, since quantum mechanics forbids the loss of information. And resolving this paradox has led to radical proposals involving holography, where the information content of a volume of space can be encoded on its boundary, suggesting that our three-dimensional universe may emerge from more fundamental two-dimensional information, a concept that sounds like science fiction but arises naturally from attempts to reconcile quantum mechanics with gravity. And while these ideas remain theoretical, they highlight the extraordinary reach of quantum thinking, extending from atomic clocks to the fabric of space-time itself. And as we continue this journey, it becomes clear that quantum mechanics is not simply a theory of the small, but a framework that reshapes our understanding of reality at every scale, forcing us to abandon comfortable notions of determinism, locality, and absolute time, replacing them with a universe where probability reigns, connections transcend distance, and measurement plays an active role in shaping outcomes. And yet within this uncertainty lies remarkable order, expressed through precise equations and testable predictions that allow us to build technologies of astonishing power and sensitivity, and this duality between unpredictability and precision, between mystery and mastery, is what makes quantum mechanics both unsettling and inspiring, because it reveals a universe that is not indifferent but responsive, not static but participatory. And as we move toward the next chapter, where entanglement, non-locality, and the future of quantum technology take center stage, we carry with us a deeper appreciation of how the quantum world governs not only the behavior of particles, but the flow of time, the structure of information, and the tools through which humanity explores the cosmos, setting the stage for an even more profound confrontation with the true nature of reality. Now here's the question for you. What part of the country are you watching this story from? Drop your state in the comments below.